It is the 8th lesson in theory of computation. In this lesson we will learn Chomsky normal form. Because context-free language encompasses regular language, the grammar of any regular expression or automaton can be written. The reverse is not always true. For example, let X be a regular language problem. Since this language is also context-free, its grammar can be written. On the other hand, another problem Y is grammatically writable as a context-free language problem. But the finite state automaton or regular expression of problem Y cannot be written. Thus, every regular language problem such as X can be transformed into the context-free grammar. But every context-free problem such as Y may not be transformed into a regular one. Here you see the transition diagram of the problem given the deterministic finite state automaton. Let's try to write a context-free grammar of the same language problem by looking at this diagram. Considering the situation we just described, this is a solvable question. Just as we begin the process of converting deterministic finite state automata to regular expressions, we just need to write the language rule for each state. The rules on the right are the solution to this problem. That's all. Consider the following 3 grammar rules. S goes to SS or symbol 1 or epsilon. Using this grammar we can write a 1 symbol in different ways. For example, we can only use the second rule. But it's not the only way. We can choose to use the first, second and third rules, respectively. Let's take a look at this. The ways to generate the single symbol word, 1, using which grammatical rules sequentially are shown below. As can be seen, it is possible to produce words in an infinite way by combining the first and third rules. But this is not a method that can be automated. Therefore, it is no longer a problem where we can give the grammar rules to a computer and say, try all combinations and find the result. Nobody wants a program that can run forever. So we have to look at the way to standardize the rules. Chomsky normal form is an approach that emerged at this point and eliminated this problem. Formal definition. A context-free grammar G equals V capital sigma R S is said to be in Chomsky normal form if every rule in R has one of the following 3 forms. Capital A goes to capital BC, where A, B and C are elements of V, and B is not equal to S, and C is not equal to S. Capital A goes to lowercase a, where capital A is an element of V and lowercase a is an element of capital sigma. S goes to epsilon, where S is the start variable. When we revise the above grammar with Chomsky normal form, it will turn into the following grammar. Again, try to derive symbol 1. There is only one way now. But we may not always do this easily. We need a transformation method. Here we will learn a 5-step transformation method. If we write the rules briefly, we will have the steps as follows. The first, eliminate the start variable on the right. The second, eliminate all epsilon rules. The third, eliminate all unit rules. The fourth, eliminate all rules having more than 2 symbols. The fifth, eliminate all rules whose right-hand side contains exactly 2 symbols, which are not both variables. Let's look at an example on context-free grammar to Chomsky normal form. Consider the context-free grammar G equals V capital sigma R A, where V equals A B capital sigma equals 0 1. A is the start variable, and R consists of the rules. A goes to BAB or B or epsilon. B goes to 00 or epsilon. Our first rule says to eliminate the starting variable on the right. Instead, it's easier to add a new start variable that goes to the old start variable. This is how we start. The second rule says to eliminate all epsilon rules. Looking at our rules, we see two epsilons. First, we start by eliminating the capital A's going epsilon rule. However, this deletion causes some skills to be lost in our grammar. To make up for this deficiency, grammar needs to regain what it has lost. Therefore, we reconsider all rules containing A on the right. There are two such rules. S goes to A and A goes to BAB. These two rules give rise to two new rules by writing epsilon instead of A. S goes to epsilon and A goes to BB. Next, we go on by eliminating the capital B's going epsilon rule. When we reconsider all rules containing B on the right, we see three rules. A goes to BAB and B also BB. By writing epsilon instead of B's, we found three new rules. Here we show how the three newly found rules are derived. You see, we're actually obtaining 5 new rules. But we already have the rule that A goes to B. On the other hand, in the step of deleting the rule where A goes to epsilon, it is absurd to reproduce this rule. So writing these two rules has no sense. Our third rule tells us to eliminate all unit rules. There are 3 unit rules observed on the right. Among these, A goes to A rule can be deleted directly, because it does not cause any loss. The other 2 rules are deleted with the replace approach. First, we delete the rule A goes to B by writing the rule B goes to 00, where we see B on the right. Similarly, we delete the rule S goes to A by adding the right side of rule A to the right of rule S as it is. The fourth one commands to eliminate all rules having more than 2 symbols. Here, we only have the terms BAB in 2 places. To eliminate them, we need a new variable, such as C, that will contain 2 of the 3 symbols of this term. If we define that C goes to AB, we can use this C instead of AB at the end of the term BAB. In the last step, we should eliminate all rules whose right-hand side contains exactly 2 symbols, which are not both variables. The thing is, this step requires defining each terminal symbol with a variable. Since only the symbol 0 is used in our example, it is sufficient to define a variable like D and assign it to this terminal. Then we will write the name of this new variable wherever we see symbol 0 on the right. That's all. Thanks for listening.